The derivative is an operator that takes a function in and spits a new function out. Um, so the notation here's several notations here. Here's the function, and I have what's called the derivative. I'm going to call it the first derivative here because we're going to have other derivatives too. So the derivative is the function y prime, right? Sometimes we call this f prime of x. We're also calling it dy dx, or we're calling it df dx. These are all the different notations that we have for this derivative function. The derivative is telling us the slopes of tangent lines of the original function. Okay. The thing is, the derivative is a function, and it has a derivative. So if I take the derivative of the derivative, this is what's called the second derivative. And notationally, I'd either do this as y double prime, or maybe I do it as f double prime of x, or maybe I do this. I take the derivative with respect to x of the derivative, and let me simplify that. This looks like d squared y dx squared. That's the way we write the second derivative, or d squared f dx squared. Right? The d's get multiplied together, the dx's get multiplied together. Now, it's notation in a sense, but the notation makes it look like what we're doing here. The derivative with respect to x of y, and the derivative with respect to x of that thing. So that's the second derivative, and we notate it this way. Likewise, you could have the derivative of the derivative of the derivative. So you can just keep taking derivatives, because each time you take a derivative, you get a new function out. So so we have the third derivative. Derivative, I guess there's a t in there somewhere. It looks like y triple prime, or f triple prime of x, or in Leibniz notation, I would have d cubed y dx cubed. Right? That's the third derivative of y. Once you get up to fourth derivatives, the prime notation, we don't just keep writing primes. So for the fourth derivative, I would write this as y, and in parentheses as an exponent, I'd put a 4 there, or f in parentheses 4 of x. The Leibniz notation stays the same, just d4 y dx, the 4, and so on. So after the fourth derivative, I just have in parentheses the 5 here or there, or a 6, or an n, or however many derivatives I want to take. Right? Let me give you an example here. Just of some fairly simple functions that we've done so far. If I've got y equal x squared, then y prime is 2x. Y double prime is equal to, I don't think we've taken the derivative of this yet, but I mean, think about what the derivative is telling you. The derivative is telling me the slope at any point. Well, 2x, heck, that's just a line with slope 2 everywhere. Well, if the slope is 2 everywhere, then the derivative should be giving me a 2 all the time. And so y double prime is just 2. Y triple prime, well, if I think about the graph of y equals 2, I mean, that's just a constant like this. What's the slope at any point? Well, the slope here is always 0. So the third derivative here would be 0. It turns out now that the fourth derivative is also 0, and so on. With polynomials, it turns out you always end up with some derivative eventually being 0. But with other functions, as we'll see as we go on here, sometimes you just keep getting a different function each time you take the next derivative. What these higher order derivatives tell us, I mean, the first derivative tells us slopes of tangent lines. What does the second derivative tell you about the function? Well, we'll see that as we go on. It essentially tells us how it's bending. What does the third derivative tell you? Well, it tells you how the bend is changing. As we work our way through chapter 3, we'll see what these different derivatives do for us. The first derivative does a lot for us. The second derivative does some things that I think get less useful as you take further and further ones down, because it's harder to see what's going on with the original function. But anyway, there's the notion of higher order derivatives.